Okay, can you guys hear me now? So sorry, that was from YouTube. It wasn't network actually, because I could see all your chats, but it wasn't transmitting the feeds. I don't know why that happened. So it's a YouTube thing. I don't know. I don't know whatever caused that. So anyway, so we are back, and yeah, so I sent a new link. You can access it using that. All right. So once again, you are welcome. And I was already talking already in the previous. I just thank God for the chat. I was able to recognize that you could not see what was going on. So anyway, what I said previously before I noticed that was that yesterday we did, or we introduced the first principle, and I told you guys to be careful, to pay attention to it, because in all your learning, it's possible that the main question you are going to see may be just for you to apply first principle. And I want you to know that if you're told to apply first principle, you're not permitted to use any other method. And that's why you need to understand first principle properly. Now, yesterday, we started with basic questions. I'm sure you guys recognize that we did a lot of basic questions where it was quite very simple. And of course, that is how it's supposed to be in mathematics. We start from the simple, then move on to a tougher one. So in today's video, we'll be cracking some tough aspects of calculus using first principle. So I would love you to really pay attention. So now we did linear function, we did quadratic function yesterday. We differentiated those kind of functions yesterday using first principle. But now look at what we have right in front of us. An example that is not like any of what we did yesterday. And you will be asked to differentiate this using first principle. Now, I'm so sure that if you check the table you probably have of the calculus identities for differentiation, you would see a quick answer to what we have on the board. So if you are differentiating y equals to cos x, if you check the table will tell you that if you had y as cos x, then the y over the x would be minus sine x. I'm sure you have seen this somewhere. So this is established, you know this probably, but we have to make use of first principle. So that's what we want to use. So please pay real attention. Again, you understand that I'm going to be quite slow but steady. When I say slow, I mean slow to ensure that everyone can understand what we're doing. So please ensure you are following and ensure you're taking something down. You're working alongside what we're doing. All right. Now let's get right into it. So y is cos x. How do you differentiate this? Using first principle. Now, I told you yesterday you have 4 basic steps while dealing with first principle. The first is for you to make an increment of both the y variable and the x variable. So let's do that quickly. So we have y plus change in y, that's the increment, is equals to cos. Now we have x plus change in x. All right, we're done with step 1. Now let's see what is step 2. Step 2 was for us to make change in y the subject of formula. I'm sure you recollect from yesterday's introduction. Now we have change in y will be equals to cos x plus change in x minus y. And I'm sure at this place you recognize what we always do, which is that for us to say, okay, if we have something like this, then don't forget that our y was equals to cos x. So therefore, we're going to be replacing cos x with wherever we saw y. All right, good. So let's see what we do right here. Change in y now will be equals to cos x plus change in x minus cos x. Good. Now, this is where it's all going to get very interesting. All right. Now, what do we do from here? Now, I want you guys to remember something I told you. I told you this, I believe, was it last weekend or yesterday? Probably I did in both. When you're dealing with calculus, it's very vital you know your trig identities. They are very key to solving questions on calculus. So in this case now, you need to recollect your trig identities, which is something I personally taught you guys. And you have videos on it on this channel, so you can go back to refresh your mind on it. Now, looking at what we have here, there are actually two different trig identities I could use, but I'll be deciding to use the most visible one, which is the compound formula. If you go back to compound identities, you would see that when we have cos A plus B, cos A plus B was equals to what? Cos A cos B minus minus sine A sine B. This is an identity, all right, which I've always told you guys to ensure you know. Good. So when you look at this question right here, this is like a compound angle situation where we will be having our change in y. Please follow through on what we're doing. I believe you understood till this point. Now we have cos x plus dx. Applying this identity here, we'll be having cos, your A here is x, that'll be cos x, cos change in x, minus sine x, sine change in x. But don't forget, we still have a minus cos x. I'm sure you can follow me. Just follow me step by step. You won't go wrong. All right. Now, now that we have done this, the next thing to do is let's try and see if we can collect like terms, because that's probably the most visible thing to do right here. So I can see this and this, they have something common. So let me, for those that probably need me to do this, let me try and bring them together. Cos x, cos change in x, then I'll bring this minus close by so that you can see what we are doing. All right, I just rewrote it in a much proper way. Now I want to make cos x, factorize cos x out. I'll be left with cos dx minus 1 minus sine x, sine change in x. This is all change in y. All right, I'm sure you can follow through on what we are doing. It is very essential you are really following through. Now, what do we have next? Please hope I'm being very clear. Hope it's visible. Hope what I'm writing is visible to everyone, because I'm trying to see how to manage what we're doing, the board. Now, look at what we have here. We have done step number 1. We have done step number 2. All right. Now, can we now go on now to do step number 3? What is step number 3? Step number 3 is for us to divide through both sides with change in hex. I'm sure you remember that step. That was the third step. So we want to divide both with change in hex now. So change in y over change in x, that's the left hand side, is equals to all this cos x, cos dx, change in x minus 1 minus sine x, sine change in x, everything over change in hex. That's step number 3. All right, so let me split this fraction. So change in y over change in x will be equals to cos x into bracket cos change in x minus 1 over change in x minus sine x sine change in x over change in x. All right, I believe I'm permitted to do that. Now, what is the next thing? What is the next step? Can you guys recall what is the next step after what we are doing? The next step, we have done 3 of the steps. The fourth step now is for us to take the limit of both sides, as change in x will be tending to 0. So that means we're going to take the limit of both sides. I'm going to do it like this first before I split it up. So this is what we are going to do as step number 4. So you do change in y over change in x being equals to you take the limit of both sides. Let me put all of this in one big beautiful bracket. All right, this is step number 4. You can see exactly what I just did. So I took the limit of both sides. Now, this is now the next thing you have to do. I want to clean up the initial thing. So now that we have this, what do we do next? You understand the rules around limits. We can split these fractions. It's permitted for us to split it this way. That means I can take the limit of, I can split out cos x and apply the limit to this, also apply the limit to this separately. Look at what I'm trying to explain right here. So I'm permitted to do this. Of course, you understand already that all of this will transform to what? The y over the x. We did that yesterday. So let's just let's change that right away. So now I want to apply this is one of the laws of limits. I'm permitted to do this. Look at what I'm doing. I'm splitting it. So now I'm having cos the x minus 1 over change in x. You can see what I'm doing. I'm splitting it. I'm splitting what we have here. So I've splitted this fraction. So cos is the same thing. This and this is the same thing. I just splitted it. So we have cos the x minus 1 over the x as one side, then cos x as one side. So I'm applying the limit to both sides. You see, I took the limit of both sides. So I'm not doing anything wrong. So I can do the same here also. I can split this one. There's a minus here, so minus. I will also split. As change in x tends to 0, I will split sine x. Can you see it? Step by step. Don't be in haste. Just move accordingly. Change in x tending to 0, I split for the other side. I have sine change in x over change in x. All right. Now this is quite beautiful. We have gotten to a very good spot. Now, of course, the limit of a constant, that means where you don't have the x here. So the limit of this will be the same thing because you do not have change in x there. There's no change in x here, so it's more like a constant. This is a constant, so the limit of this will be cos x. That's settled. The same thing goes here. The limit of this will be sine x. That's settled. So let's talk about these two, the limit of this and the limit of this. Now please pay real attention, and I'm going to remind you of something quickly, and you would confirm with me. Now look at something going on here. I'm going to write this thing here on this side. Look at something. Do you remember this? Do anybody remember this? Do anybody remember we solved something like this in one of our previous classes? Limit of x tending to 0 sine x over x. If you remember we solved something like this, recollect that we got the answer to be 1. I can solve it right away. There's no big deal about it. But I need to tell you that sometimes for you to be able to solve quickly, especially in exam hall where you have you are constrained with time, you want to remember some of these things. So if you use L'Hopital rule, you will get this quite as 1. Limit of x tending to 0 of this is 1. So look at this. If you look at this, you observe that this and this, they look alike, just with the difference of instead of x now you have change in x, which doesn't really matter. X here is change in x. You could have x as u in another equation. That means I could even say u tending to 0 sine u over u. The question is, do I need to go on to resolving this? No, I know that since it follows this pattern, the exact pattern, it will be equal to 1 also. If it was p that was here, limit as p tending to 0 of sine p over p is also going to be 1. So that tells me already that the limit of change in x tending to 0 of sine change in x over change in x will also be 1. All right. So you can see what's going on there. So all this thing here will turn to 1 on the basis of this. if we had time and you wanted us to do it, we can go on to solve this. We can go on to solve this. All right. Now, I've established that for this. Let's try and establish for this also. Look at something going on here. This is similar to you having, I don't know how to, where I should carry you to explain this. If you have it, I want you to know that the limit of this, look at, I want to use this to establish that point also. So just follow through on what I'm doing. So when you have the limit of you know, we're dealing with cos, if we have 1 minus cos x over x, this is equals to 0. The limit of this, please look, try and pay attention to what we're doing. Look at what I wrote. It's not the same thing. I'm sure you all agree with me, it's not the same thing. But I want to get this, I want you to hold it tight and know it properly. Now, if you look at what we have there, you can see clearly that we said the limit of course, if you want to prove this, use your L'Hopital rule immediately. I'm sure you are very much great in using L'Hopital rule already. So use L'Hopital rule, find this out. You will see you get your answer to be 0. Of course, you differentiate this. This will give you sine x. Differentiate this will give you 1. As x tends to 0, sine 0 is 0. That's perfect. You understand that already. So if you look at this and this, they are very, note this thing because later you'll be needing it for quick solutions. That's why I'm writing it down like this. So this is very similar to this, more like you had it's more like you had minus 1 minus cos x over x. So in the end, it's like minus 0. It's like you have, bring out minus, you have limits of x tending to 0. It's like, if I wanted to use cos, this and this are the same thing. That means minus 1 minus cos x over x is the same thing as 1 minus cos x over x. You can do the math quickly. Minus comes here, will be, sorry, what did I write? This would be, there should be a plus here. It looks like I'm confusing myself right here. So anyway, what I'm trying to bring out here is that this solution will give you 0. And you can go on to prove it right, because you don't even need to use this, but I really want you to remember this. But you don't really need to use this, because if you go on to use L'Hopital rule to solve this, you will get cos minus sine dx over 1. And then if the x is tending to 0, you'll be having, is more like you use L'Hopital rule, you have minus sine dx over 1. That will be after differentiating. All right. So if you're done differentiating this, exactly. Thank you, that person that wrote the chart. What I was writing, I was supposed to write this back. Sorry, the mistake I made was I was supposed to write this. So it was supposed to be minus cos x minus 1. Yes, this was what I was trying to write. Sorry for that. So now, anyway, all I was, you don't even need to follow this if you don't have to follow this. You can do it straight away. You will still get minus sine 0 over 1. This will still give you 0. So all I wanted to prove, all in all, is that all this, what we have here, will turn to 0. You can use your L'Hopital rule to prove it. It will give you 0, because you differentiate the numerator, you will get minus sine dx. Differentiate the denominator, you will get the x. You get 1. If you put in the x tending to 0, you get sine 0 over 1, which is minus 0, which is 0, essentially 0. So all this was just to ensure that you can understand the next thing I want to write, which would be, now we can have it like this. Of course, I told you this is a constant, so we'll be having cos x. Then all this now will turn to 0. dot 0, then minus, all this will turn to sine x. I told you already, this is like a constant. It's a constant. It's like, for those of you not understanding what was going on, it's a constant because you do not have the hex, sorry, change in x. I think I always say the hex. It's actually change in x. You don't have change in x in this expression. So sine x is different from sine change in x. Since you don't have change in x here, this is seen as a constant. All right, it's like if you say the limit of 4 when x is tending to 0 is 4. These are some of the properties around limits. So this is like a constant. So you cannot apply change in x tending to 0 inside this. So this will still be sine x. And then for this one, we already proved it to be 1. So we can see right now, you can see this is cos x dot 0, which will be 0 minus sine x, which will give you what? Minus sine x. So do you see the process? You see the process? Quite very, very simple. So now we want to go to the other side of things. I believe you all agree with me that from your table, which I showed you initially, if you differentiate cos x, you get minus sine x. So let's do for when we're differentiating y being equals to sine x. Please, you will have to write quickly because I want us to go deeper into I want us to go deeper into calculus today. So let's try and move quickly. So we have y being equals to sine x. Let's try for this. These are the kind of questions you should be expecting if I'm going to ask you question. I don't know what this person is saying. Somebody said it's not correct. What's not correct? What are you talking about? All right. So y is sine x. Now, we don't need to say so much. If you remember your table of differentiation, if you differentiate sine x, you get cos x. If you differentiate cos x, you get minus sine x. We have proven for this. Let's try and see if this will work. So our final answer here is supposed to give us cos x. If we are correct, we're supposed to use first principle. So we're not just using the general format here. So again, you have to go with the first step, which would be this. This is the first step. I believe everybody could always do this. It's quite very simple. What's step number 2? Make change in y the subject of formula. All right. Because of time, I'm sure you remember what we're going to do next. We're going to put in our y as sine x, since y is sine x. All right. So now we are back at this point again, where you need to remember your trig identities. If you don't know your trig identities, these are going to be very, very difficult to solve because at this there's nothing else you want to be doing here than using your trig identities. So what do you want to do right here? You want to recollect that sine a plus b, which I believe some of you know already, or all of you probably. You know that your sine a plus b is equals to what? Is there anybody here that remembers it? All right. So look at that. This is your identity for sine a plus b. So the reason why I had to summon this identity is actually because I can see a compound angle situation here. This is x plus dx. So this is the identity to be using. So what do we do right here? We go on to apply the identity. So this will be what? Sine x cos change in x plus sine change in x cos x. Then don't forget we have the minus sine x. You need to be patient, you need to be careful, you need to work carefully. If you are too in haste while solving questions like this, the chances of you mixing things up are very, very high, even though you are very sure of yourself. So, the next thing we have to do, we have to try and bring our like terms together. So we have our change in y is equals to sine x cos change in x minus sine x plus cos change in x cos x. I'm trying to be fast in the writing, so please pardon that. I want us to move quite fast today. All right, so this is the resultant of what we've done. So we have done step number 1, we've done step number 2. The next step is now to divide through with change in x. So change in x and everything over change in x. That's step number 3. I believe everybody can do this, right? I believe everybody can do this. Now, having done this, the next thing is you want to, once again, as I did the last time, you want to split these things up. You want to have change in y over change in x. Look at the steps. I believe if you're really following, you would find this very easy because it's quite easy. You don't have to sweat over it once you follow the right step. You see what I just did? I splitted the fraction, right? Oh, where is the mistake? Oh yeah, you people should call it out. Where is the mistake? Where is it? Oh, it looks like I'm seeing it. Yeah, is it not here? It's here, I guess. I wrote sine. I wrote cos instead of sine. I could see that. That was. Can you see? Thank you for calling that out, and that should sound as a very great warning to you guys. You can see already that you don't have to be the you could be the best and make mistake, right? You could be the best and you can see what really just happened. That's right. That's very thank you very much for calling that out. Now so now we have corrected that. So look at what we have now. That means you guys are following. I really love that. So what we want to do next, which is the next step, the 4th step, is to take the limit of both sides. So let's take the limit of both sides now. We take the limit of this as change in x is tending to 0. That's change in y over change in x is equals to the limit of change in x tending to 0 of all this. So we have sine x cos change in x minus 1 over change in x plus sine change in x cos x over change in x. All right. So now we have to split all these things up, and I'm sure you understand that all this will turn to what? The y over the x. I'm sure you guys are flowing with that. Now all this is synonymous with the y over the x. Good. Now equals to, let's now split this up. So we split, I'm sure you follow, if you follow the last one we did, you can see you split it up like this. You write your sine x here, and you split for the other side. Limit as change in x tending to 0. You have cos change in x minus 1 over change in x. I'm sure you can follow. We just have to be a bit fast today so that we can cover much. Your exam is very close. And in this case now, I'll be separating cos x and leaving sine dx over dx. And I'm sure if you follow the last example, you know why I'm doing that. So this will be cos x. Then I'll be having limit of the change in x tending to 0. Now I'll be having sine change in x over change in x. Of course, you know already that one of the reasons why I did this is because, and this is the reason why you have to be very familiar with all these your identities. The reason why I did this, what I have here, is because I recollect that the limit, this is something that we have solved already, of x tending to 0 of sine x over x. is 1. So when I saw something like this, I want to bring this together so that I can have something like this. It's not something you did it intentionally. So I wanted to see this come out so that I can easily turn this to be 1. So I also, you can see this thing which we tackled last time. It's also here again. So I'm sure at this point, everybody here knows exactly what this will turn to. This one here will turn to 1. We turn to 0. This will be 0. And this one right here will turn to 1. I explained it in the last example. So we don't need to go through that again. Now, what we just have to do now is to reconcile every of all these things together now. So we have the y over the x, which is what we're interested in, is equals to, I told you already, this is the limit of a constant because there is no dx here. So taking the limit of this is still the same, going to be the same thing as sine x. So this is still sine x dot, that's times all these terms to 0 as I explained already, that's times 0, then plus, this is also going to be seen as a constant. So that will be cos x, then all these terms to what? To 1 times 1. So looking at what we have here, all these terms to 0 because anything times 0 is 0 plus cos x. So that means the y over the x is equals to cos x. Are you seeing that? This is so nice. I feel you guys are so, if you are really flowing, you cannot feel this cos. I just don't think so. Because this is very clear. I believe this is clear enough. So now let's move further because this is not the only examples you can have. Let's use a different example now. And very soon we'll get into exponential functions and you will learn more. And one thing I need you to understand is it is all this basic knowledge, everything we're doing, the fact that you are very professional, you know it very well. This is what will make you to be able to tackle the difficult ones later. So please, I hope I'm not too fast for anybody. So we have y equals to tan x. Again, I said I want us to tackle a couple of questions today. I want you guys to be exposed to several possibilities in calculus under these aspects. So I hope I'm not too fast for anybody. If I'm too fast, you let me know so I can probably cool down a bit. All right. Now we have y equals to tan x. Can you imagine you seeing this in your theory question? And they just said using first principle, find the y dx, and they gave you this function y equals to tan x. What exactly are you going to do? First of all, by the way, if you are yet to give this video a thumbs up, please do that very quickly. It costs you nothing. All right. Now y equals to tan x. So yes, look at something that will happen. I'm sure you guys will try and do this. I'm sure if I give you this question now, many of you will follow this attempt, and you're not wrong. You're not wrong at all. You're not wrong at all. If you do it that way, I will tell you how to still move on from that angle. So one of the things based on what we have been doing, this is going to be the approach of literally everybody in this class, and that will not be wrong. Now, y plus change in x, of course, we're increasing both the x and the y variable. So we have increased the x variable, we have increased the y variable. Now, but because for the sake of some of you that may not really flow with too many complex expressions, I would love you to have done this initially. Sin x over cos x. Again, can you imagine you do not know trig identities? I'm sure, I believe everybody in this class really understands this identity. That y equals to tan x is the same thing as y equals to sin x over cos x. Trig identities plays a very key role in solving these questions. Now, look at what we have here. You can start from here. I would love you to start from here, but you can also continue from here. Because why not? If you said tan of an angle is equals to sine of that angle over cos of that angle, that means I can still move on from here to write that tan of this angle now will be equals to sine x plus change in x over cos x plus change in x. All right. This is still correct. But imagine you started from here, which is also nice. You could have moved on from here by increasing both the y variable and the x variable. Whichever one is okay. So I can go on to say y plus change in y equals to sine, of course, x plus change in x over cos x plus change in x. So in the end, we are still on the same place. We arrived at the same place. So now, I'm sure you have been able to all arrive at this. This is quite easy. Now, the next thing, which is the next step, is for you to make change in y the subject of formula, which will be for you to write sine x plus change in x over cos x plus change in x minus y. These are basic steps which I'm sure everybody really understand. So we have change in y being equals to, of course, you know what we're doing next. We are substituting y for whatever y was initially. Don't forget, it's not going to be nice at this point for you to be writing your y as tan x. The reason is because you have already substituted tan x for sine x over cos x. So at this point, you do not want to write tan x now, even though you are not wrong. But in the end, if you even wrote it like this, you will still have needed to have substituted it for sine x over cos x, because we want to put things in the same order so that we'll be able to move more fluently. Now we have gotten to a place where I believe everybody can relate. I'm not sure anybody is not following at this point. So again, what do you do at this point? Very simple. You don't have to panic. Just keep moving. What do you have to do? What you have to do is to take the LCM of both sides. Is there any other thing you can think of that will get you going at this point? Not really. So go on to take the LCM of both sides and take it carefully. So the LCM will obviously be the product of these two. That will be cos x plus change in x, then cos x. Both of them are going to be the LCM. So you go on to say this goes in this, you'll be left with this. That will be cos x, and then you'll be left with multiplying it with sine x plus change in x. That's the numerator. Then you have minus sine x, multiplying it with the, you understand that part. I'm sure nobody is here being confused. Cos x plus change in x. All right, step by step, you will not go wrong. This is something I believe everybody can do right in this class. I believe there's nobody that is going to find it difficult to do what I've just done. Just finding the LCM and do it carefully. All right. So what do we do next? So what you want to do next now is you want to make all these things, you want to open them, right? You want to open them because I believe that's the most visible step to take. So when you're at moments like this, you want to be sure of ensuring that there is no okay, look at me. I said we wanted to open something. Before we even open this, are you seeing something here? As in, for anybody that doesn't understand trigger identities here, they're going to have serious issues, because I don't look at trigger identity here being needed because this is another compound formula. So of course we are applying this sign. Let me just write it directly. Of course, this is change in y will be equals to cos x multiplied by, now let's apply the compound formula for this. What's it going to be? This will be, I want to use a bracket because this is compound. This is a compound expression. So I'll be having sine x, then cos dx. This is trigger identity I'm applying here, plus sine change in x, cos x. All right, this is just for this one. Oh, this is just for this one. Okay. So minus, once you know what you are doing, just keep doing it. You don't need to panic. Minus sine x, then I'm multiplying. I want to do the trig identity for this one. So what's the trig identity for this one? I'm sure you know this one. This will be cos x, cos change in x, minus sine x, sine change in x. All right, can you see that? So permit me to just write as we did yesterday when we have situation like, let me just be writing denominator there. I'll just be writing DEM. Okay, let me still write the full thing for those that don't yet understand what we are doing. If I write that, but you understand this is where we are at, right? So look at this. Step by step, you will not go wrong. Don't forget, we're trying to find the differentiation when we had y being equals to tan x. Good. So we have gotten to this place. So at this point now, step by step, you won't go wrong. Just open this bracket now. Open it. It will look complex, but just open it. You don't have to be afraid. When you're in a stage like this, you are doing calculus. Don't be afraid of complex expression. It's calculus. It's not the normal expressions. So you'll be having things like this. So changing y is equals to, I want to open all this bracket now. So this will be cos x, then sine x, then cos change in x, plus, then I have, this will be cos square x, because cos x times cos x will be cos square x. This is not the same thing as cos x square. This is cos x times cos x. Then we have sine change in x. All right, that's for this side. So let's do for the other side. So we have minus, because there's a minus sign here, sine x times cos x, that will be minus sine x cos x, then cos change in x. Then minus times minus now will turn to plus. Sine x times sine x will be sine square x, then sine change in x. Now, the biggest pitfall for many students at this point in questions like this is errors. When you have error in your work, there's a way things will just not work out. Because normally some of these things, if you look at them, like if you look at what's happening right here now, look at something, you can see something going on now. This is sine x cos dx. This is sine x cos dx. And you see these two things are the same things, like having x minus x. So you know what will happen in that kind of situation? X minus x. In this case, let's say a minus a. These two will cancel each other. Are you seeing that? So this expression will cancel this expression. Can you see how a very complex expression has been reduced down to a more simpler expression? Are you seeing that? So now change in y will be equals to, all this is going out, we are left with cos square x sine change in x, then plus sine square x sine change in x. Everything over the denominator, which is cos x plus change in x, then cos x. This is how it's, you have to be very confident when solving. You never can tell what's going to happen. Now, look at what's going on right now. Look at what's going on now. We have sine dx here, we have sine dx here. So one of the things we can do now is to factorize sine change in x. And then we'll be left with cos square x plus sine square x. Everything over what we have here. Cos x plus change in x, cos x. Do you see how we are moving, making real progress? And you have to do it step by step and don't mix things up. Now, again, once you have issues with trigonometry identities, there is going to be serious issues in your calculus. I'm sure you guys can see what's going on here. This is a trig identity, what we have here, and this will be equals to something. If you remember it, you can type it in the chat box. This will be equals to 1. All right. So now that means I'm left with my change in y being equals to sine change in x over what I have here, cos x plus change in x, cos x. So this is using the first principle. Yes. Now, here we are we have been able to we are done with step number 3. You see, we just got done with step number 3. Sorry, step number 2. Step number 2. We just got done with step number 2. So we have to go on to do step number 3, which is for us to divide through with change in x. So this is what I'm going to just do so that we can, I believe you all know what's going on here. So I'm going to divide through this way. I'm just going to write divided by change in x here. I'm going to write the sign here, change in x. All right. I'm sure you're seeing what's going on there. Now, this can move on to multiplication, and then we'll be having times 1 over change in x. I'm sure you can all flow with what we are doing. So this means that I can write my dy over dx as sine change in x over change in x. Of course, this times all this. That will be cos x plus change in x, then cos x. You see that? So we have that right here now. And it's now time for us to move straight into our last step, which is step number 4. All right, what is step number 4? Step number 4 is for us to now take the limit of both sides when change in x is approaching tending to 0. All right, so let me see how that will be written. So we are taking the limit as change in x tend to 0 of change in y over change in x. That's for this side. So you take the limit of both sides. So we're taking the limit of all this. So sine change in x over change in x cos x plus change in x cos x. So you know already that all this will come on to dy over dx being equals to what? Now, this is where you have to do it again. You have to, as much as you can, split this. So look at how we're going to split this. Just pay attention to the splitting now. You know, you have to be familiar with your identities. Which will really help. It will really help you a lot. Now, I know that when I take the limit of change in x tend to 0 of sine change in x over change in x, I know I get 1 there. So I'm going to make the arrangement to try to bring that into fruition. So I'm going to have this. So I've extracted this. I'm going to, of course, these are some of the properties of limit. It's permitted. So this other one will be left with 1 over cos x plus change in x cos x. If you can see what just happened, I just splitted the whole expression. I brought sine change in x over change in x to one side, then I'm left with 1 over cos x plus change in x cos x. I brought that to one side, to another side, and I'm taking the limit of both. So you have not done anything wrong. We are still on the right path. This is using first principle. All right. If you're not told to use first principle, you don't have to go through all this. But if you have to go through first principle, then you have to go through all this. So this is using first principle. All right. Hence the length. That generally, first look at the last question we solved yesterday. If we're using the general principle, we would not use 5 seconds or thereabout to give us our answer. But first principle, you would use almost 10 minutes. So that's why the question used to come out as using first principle. Solve. In that case, you are not permitted to use any other method apart from first principle. So of course, you know what happens here. All these will turn to 1. So we have the y over the x will be equals to 1 dot. Now, change in x is tending to 0 here. That means you are going to be fixing wherever you see change in x, you should be putting 0. That will be cos x plus 0 cos x. Can you see where we have arrived at? All right. So what's this going to be? This will be, of course, 1 times 1 is 1. That will be 1 over cos x plus 0. That will be cos x, then cos x. So I'm sure you can see that at this point now, we can write the y over the x to be equals to 1 over cos square x. All right. Then now look at what we're going to do. Is equals to 1 over cos square x. I'm sure you agree with me that this is the same thing as I can write it like this. I'm sure you agree with me because this is the same thing as this. This is the same thing as this. They are the same thing. Now, once again, if you have issues with trig identities, you would have really issues with calculus. If you remember and recollect under trigonometry, you will remember that sec of an angle, the second of an angle is the same thing as 1 over the cos of the same angle. This means already that this is the same thing as sec x all square, which is the same thing as sec square x. And this tells us already that when you have y being equals to tan x, the y over the x of this is sec square x. So these are the kind of questions you should be expecting. Whatever tests you this much, you should understand that it's the kind of questions when you are under A level that you should be expecting. Of course, you are not doing O level, so you are doing calculus. There are much more elaborate questions than all this, by the way. There are questions where there are questions where you would have much more longer expressions. This is quite still even small. Calculus is broad, all right? So now I'm going to give you something to solve quickly. I want to see you, now that I have done on that, I want to see you try this also. Well, of course, I'll be solving here, but let me see you now make the right attempt. Now, look at what we have now. We have y equals to sine square x. Sine square x. So can you differentiate this using first principle, by the way? Can you differentiate this using first principle? Y equals to sine square x. Can you differentiate this using first principle? Using first principle. Now, let me say one thing. It's very good practice for you to know your answer using the general formula if you are in an exam, or so that you will know exactly where you're heading towards. So you will know if you're correct or not before leaving the exam hall. So when you have y equals to sine square x, can you quickly, before you go into using first principle, can you try and use the general rule? So how do you differentiate this using the general rule? Now, I don't know if, do you think there's an identity for this? I don't believe there's an identity for this. So how do you solve this using the general rule? Do anybody know that presently here? Using the general rule, can you solve this using the general method? Of course, it's quite very simple. What you have to do initially is to rewrite this as sine x all square, which is the same thing as sine square x. All right. Now, look at what I explained to you yesterday. In this case now, you cannot go on to use just anything. You have to use chain rule. You have to use chain rule, not product rule, chain rule. You can use product rule if you want to use sine x times sine x, which is quite, that, of course, that's possible, but maybe not very advised to, because that may probably be longer. For chain rule, what you have to do is, if you recollect, I probably will still explain all these rules: chain rule, product rule, quotient rule. I will explain those things probably some classes ahead of us. So, but look at what we're doing here. We'll take sine x as u, so we'll say y equals to u squared. So u is equals to sine x, obviously, right? So if we want to find the y over the x of this expression, we want to find the y over the x of this expression, it will be equals to the y over the u dot the u over the x. I've explained this in previous classes. So this is what we want to solve to get the y over the x. So we have to go on to find the y over the u, and we have to go on to find the u over the x. So what is the y over the u? The y over the u is obviously 2u. Very simple. The y over the u, we are differentiating the y with respect to u. That will be 2u. And what is the u over the x? The u over the x, u is sine x. So what's the u over the x? The u over the x is what? If you differentiate sine x, you get cos x. So we bring these two together. So that means the y over the x will be equals to the y over the u. That will be 2u dot the u over the x. That's cos x. So what is u? U was sine x. So you go on to fill that. That will be 2 sine x cos x. So this is my answer using chain rule. Can you see that? Using chain rule now, I've been able to get the answer to be 2 sine x cos x, right? Good. Now, this is simple. This is direct. Go on now to use first principle to solve this, and let's see how much you are able to go on doing this. All right. So this is the answer using chain rule. For those of you that did not get the answer, you can follow the process. Very soon we'll go into all this later, but for now, we're still focusing on just first principle. So how do you do this using first principle? Well, you can go on solving yours while I will be doing the application here. So let's go on. Let's solve together. You can be doing yours, by the way. So I'm following the first step, which is basic. You're going to fill in. You are going to increase both the x and y variable. And then the next step, which is step number 2, you are going to go on to make change in y the subject of formula. All right. And you know the next thing to do here. I'm sure everybody can do this, what I just did. I'm sure nobody is having any issue doing this. Now, this is the place where you need to pay attention. Look at what is going on here. There is something you should be able to see, which we have always used in these classes. Now, this is a good example of what we call difference of two squares. This is a square, this is a square. Just in case you don't know, let me write this better for you. This is the same thing as sine x plus change in x, everything all square, minus sine x, everything all square. So you can see this is difference of two squares. So the way you do this, obviously, is for you to go on to apply the change in the difference of two squares formula, which will be change in y is equals to, if you remember, just let me write it here for you. A square minus b square is equals to a plus b and a minus b. All right, that is default when dealing with algebra, right? So that means in this case now, you'll be having sine x plus change in x plus sine x. That's this side of things. I'm doing a plus b now. That's it. Then I have this a minus b, sine x plus change in x minus sine x. I'm doing this side of things. So that's me applying difference of two squares. All right. So now, I believe you were able to follow that. Don't forget the answer we got there. We got 2 sine x cos x. So you can go on to keep solving, those of you that are solving. So I believe this is quite understandable. And what's the next thing you can do right here, now that you have gotten this? So obviously you want to see how to make these expressions much more decomplexed, and that's with you have to go on to apply your compound rule. Please, whenever you're solving questions like this, I beg you, be patient. You have to take your time. So we have been able to express, if you follow this step, we have gotten to this place right now. So I can see compound angle happening here. I need to go on to make it less complex, less compound. So what do I do? Well, I would change this up to sine. This will be sine x cos change in x, then plus sine change in x, then cos x. That's just for this one. Just for this one is what we have here. Then I now add this plus sine x. All right, you see that. you do it step by step. You cannot be in haste when solving using first principle. You may be so lucky that this is the question they will just bring out in your exam, in your main exam. And they just bring out, they will say you should use first principle to differentiate this. And if you have paid attention real good, it's very simple at that point. So you do the same thing here. Sine x cos change in x plus sine change in x cos x. But in this case, this one is for this. This is what we just wrote. So this will be minus. You will add the minus there, minus sine x. Good. So this is great. Now, what do we want to do next? We want to divide through by changing x. We have been able to do step 1 and step 2. So let's go on to do step 3. We want to divide through by changing x. So divide through by changing x. Of course, we divide this by also changing x. Good. Now, I'm sure you are following. We can go on to, of course, try to bring out collect like terms. Look at changing y over changing x. For those of you looking at things, please make sure you follow through. You can see right here that we have this and we have this. So we'll bring both of them together and just make it sine x. Then we'll bring this will be cos changing x plus 1. I'm sure you understand. I'm factorizing sine x out, and I'm left with plus sine changing x cos x. That's this one here. All right. Put this in a bracket. Let me do for this other one also. Now you can see right here that we have this and this as like terms. All right. You can see sine x is common to both. So we can go on to bring out sine x, and then we are left with cos changing x now minus 1, because minus 1. So if we have minus 1 here, then we have this left over being written here, plus sine changing x cos x. Good. So now all divided by changing x. All right. So this is making sense, I guess. So now look at something going on here. I want to just quickly, because I don't want you guys to get confused. Look at what I'm going to do. This is multiplication going on here. This is something times something divided by something. More like, imagine I have a times b, everything over 2. I'm sure you know that I can write this as a over 2 times b, or I can write this as a dot b over 2. It's still the same thing. So what I want to do is that I want to hold this change in x with any one of them. I'll be holding with this one. So I want to hold it with, look at what I just explained. This is this times this over change in x. I can decide to do it like a over 2 times b is still correct. I can say a times b over 2 is still correct. Whichever way you pass through, you are still correct. So I'm going to use it this way. Look at exactly what I'm going to do. Just try and pay attention. You will see what's going to happen now. So don't forget, we're trying to differentiate sine square x. We've gotten it using the chain rule, but we want to use the first principle at this point. So look at what is happening right here now. We have change in y over change in x is equals to sine x cos change in x plus 1. Then we have the plus sine change in x cos x. We put this in one bracket. All right. Now, this other one also, we're going to put this in one bracket also. So we have sine x. I'm writing this. Then we have cos change in x minus 1. Then we have plus sine change in x, then cos x. Now I'm going to be dividing this one with the change in x. All right. So that's what I wanted to show you guys. So just because I don't want to, I want to, you know what I've done already. So imagine I wanted to write this again. This is the next thing I will now write. I will now split that and change the next in two of the places. Okay, because this one is plus. So I can, it's like if I have a plus b over 2, it's the same thing as a over 2 plus b over 2. So that's what I want to do now. I just didn't want to rewrite that again. So, you know, it was everything over changing x. So I'm splitting it now, changing x on this side and changing x on this side, just because of time. So now, if you can follow what I'm doing, so the next step now after doing all this is for me to now take the limit. You know, we have done step 1, we have done step 2, we have done step 3. Now we have to take the limit of both sides, right? So we want to take the limit of both sides. We take the limit of the left-hand side as change in x is tending to 0. We have change in y over change in x will be equals to the limit change in x tending to 0. Permit me to just write everything here. Permit me to just write this. Please permit me. I don't want to rewrite all this. So everything we have here, we're taking the limit of this. Right? I didn't ask you to write that in your exam, or please. Oh. This is just me trying to save. I'm trying to save time. All right. But you can imagine when you're in the exam or you don't have to save time, you have to write everything because you do not know which will hold the mark you are looking for. All right. So now I want to split this limit. You know how we do it. We go on to split the limit. Very, very important. You need to split all the limits now. So I want to, this limit, don't forget, this limit applies to everything here. So I will split the limit. I will split for sine x. I will split for this one. I will split for this one. I will split for this one. I will split for everything. So when we're done doing it, you will see the resultant of it, right? So let's start to split. We have to write down so that everybody can follow. We have to write all the splitting. So all this thing we have here, all this one here, I'm sure you know that this will turn to the y over the x. So this will be equals to, I'm taking limit of everything here. So that means limit as change in x is tending to 0. I will first have sine x. That's the first split. Then I will split again to have limit as change in x is tending to 0. I will have for cos change in x plus 1. That's the second split. Now I will split again. There is a plus. I will split change in x tending to 0 for sine change in x. That's for this side. Then I will split again, limit change in x tending to 0 of cos x. So I'm going to split for every one of them so you can be seeing the result. So, and look at this one. For this side now, I'm done with this side. So there's a times here now. It is times. I'm sure you know there's a times in between this. So there's a times here. So I'll take the limit. In this case, I'll just do for sine x. So of sine x, change in x tending to 0. Then I will also do for this side the limit as change in x is tending to 0 of cos change in x minus 1 over change in x. I'm sure somebody there is not too surprised of why I did this. That's why I said you have to be very familiar with the things you are doing. The reason why I did this is because I already did something in this class. That was when we just started, of which this will turn to 0. I know already that this will be equivalent to 0, minus 0, which is 0. All right. So minus 0 is 0. So I'm left with just this side. Let me write that one on this side. Let me write plus. Now look at what I'm going to do. I'm doing for this side. I've done till this point. I want to take the limit as change in x is tending to 0 of sine dx now over dx. You see, in this case, look at what happened here. In this case, I did not put the hex here. Look at the wisdom. I think I want you guys to be very smart about this. Look at the wisdom. This is where This is where the smart guys will come much better than people that are not paying real attention. if you look at what's going on here, I had sine x cos this cos the x minus 1 over the x, over change in x rather, and I had the same thing happening here. When I got here, I said sine x, I splitted sine x, I did not put over the x, I did not apply the change in x rather with it. The reason why I did this was because I knew that if I attached it to this cos change in x minus 1, this will produce 0, which I knew already. Now, in this other case now, I'm attaching change in x to the sine change in x because I know that this will produce 1. So that is one of the things that will come if you have practiced enough. You would know all these things. So you see, you see the way I splitted it because I want to see my answer. So if you did the opposite, you may not see your answer. Like if you went on to put change in x here, which is still mathematical to do that, but obviously it's not going to produce the right answer for you. If you put change in x here, then this will turn to something else. If you put change in x here, this will turn to something else. So you have to follow based on, that's why you have to practice so that all these things are much more easier for you. So look at what we are doing right here. We have the y over the x being equals to, I'm sure you know what this will turn to. This is a constant in this case because we do not have change in x here. So this will still be sine x, all right? So this is sine x. And look at this. Change in x is tending to 0. Put in 0 here. That will be cos 0 plus 1. Let me write that as that's times cos 0. What is cos 0? Cos 0 is 1. But let me just write it there for people that need to see. Cos 0 plus 1 plus limit of this will be 0 because this is sine 0. You put in change in x as 0, this will be sine 0. Sine 0 is what? 0. I think I can write that directly. For this one, I can write this also directly. But let me just still put it like this so that I'll come back to explain it perfectly. So looking at this, this will be, there's a times here. This is change in x tending to 0 of, this is a constant because there's no change in x here. This will be cos x. Are you sure I want to be sure you are following? This is how meticulous you have to be when solving. So there's a multiplication here also. Multiplication. Change in x is not here. So we're going to be having sine x. All right. Just for clarity, let me put this bracket here so that you guys can understand what's going on. There's a bracket here, then this other one is happening. All right, let's use our bracket well. So this one will be sine x. All this will turn to 0. We said this already. This will turn to 0. We did this already earlier. This will turn to 0. Then we have the plus. This will turn to 1. That'll be 1 times, this will be cos x because this is a constant also. Can you see how we have been able to deal with this voluminous work? Because of understanding. Once you understand limits properly, you will be able to do all these things I have just done. Now, let me come back to this place now. Cos 0 is 1. If you press that on your calculator, cos 0 is 1. So this will be 1. That will be 1 plus 1. So 1 plus 1 will be what? 2. All right. So look at it now. The y over the x will be equals to what? 2 sine x plus 0 times anything is 0 plus 0. So that goes away. All right. Times sine x times 0. Let's put this in a bracket. Times sine x times 0 is 0. That will be 0 plus 1 times cos x. That's cos x. 0 plus cos x is cos x. So cos x. This means the final answer is what? 2 sine x cos x. I think this is the place where you guys should give me a round of applause. Can you see exactly what I'm saying? We did this using chain rule. We arrived at 2 sine x cos x. We went through using product rule and we are arriving at the same answer. Once you get a different answer using first principle, you are not going to be correct. You must get the same answer. And it's very good practice that while you are solving, before you solve, you can go on to use the first easier rule, that means the general rule, to solve, so that at least you will be on the right pathway. All right. So please, you can go through all the solution, and you can follow through on every one of them. And if you have questions, you can always reach out to me. It's quite very, very simple. So now we'll be going to natural logarithms around differentiation. And I want you to really pay attention. I will be giving some insight around the theory around natural logarithms. And it's very important you pay real attention. So under natural logarithms, you may be seeing things like exponential and everything. So let's get started, right? So all right, so we're done with this. I don't think anybody has any issue here. This is how we solve. So we have been able to use first principle with basic expressions, basic equation. We've been able to use first principle now with circular functions. We have done for sine x, for cos x, we have done for tan x, we have done for sine square x, we have done for whichever one we have not done for. I think you can go on to try that out. Now, let's go on to using first principle for natural logarithm. So, for instance, let's say you have a question that y is equals to ln 3x. Ln 3x. All right. So, these are interesting plates, and you need to be very attentive because these are very key aspects of calculus. Once you understand all these basics, it makes your work very, very easy. So we have there are some things I would love to first talk to you about before going into the first expression. So now, guys, when you are dealing with calculus, you may see something like this. Look at this. Log E x. You see something like this. And you may also see something like this. Ln x. So I want to give you the understanding of this. So these two things, they are the same thing. This is natural logarithm of x. And it represents the power to which e. Like for instance, imagine I said y is equals to log ex. All right. So I said it represents the power to which e must be raised to equal a given number. So e raised to power y is equals to what? X. So I'm sure you understand a little bit around logarithm. It represents the power to which e must be raised to equal a given number, right? Now, there are some things I want to quickly tell you, which is number one. When you have, when you see this e, note these things because I do not know where you may need them. Note these little things, that the natural logarithm of e is equals to 1. Note that somewhere. Also note that the natural logarithm of 1 is equals to 0. And also note that the natural logarithm of e raised to power x is equals to x. Just note this anyhow and anywhere you want to. Very important things. You may meet them tomorrow. You may see an expression tomorrow in which you may want to apply this any of these things. Maybe you got to a place and you are seeing lane E. In that case, you quickly fix in 1 there because lane E is 1. Now, something else I want to bring to your notice. I'm sure you have written this down. Because before we go on to solving, identities makes your work easy. So we have to sometimes define some identities. So I will define 2 identities very quickly so that while we're solving, you'll be able to make use of them. All right. So look at this. We have, this is an identity I want to give to you. Imagine you have this. The limit of ln 1 plus u over u. Look at this. Please try and look at this very well so that you'll be able to understand. You'll be able to understand what's going on. Look at, you're taking a limit of u tending to 0, the natural logarithm of 1 plus u over u. When you see anything of this sort, always know that it's equal to 1. This is an identity I want you to know. All right? It's an identity I want you to take note of, number 1. So when I call on this whenever we are solving, please don't ask. It's an identity that you may need to know. Number 2, I want you to note also, you can write all this somewhere. You can write it somewhere. You can easily call it back. If you have the limit of, let's use another alphabet now, h tending to 0 of e raised to power h minus 1 over h now. Look at this now. Look at the difference. You're taking the limit as h is tending to 0 of e raised to power h minus 1 over h. If you see a situation like this also, it also equals to 1. So these are things that will make your work easy. Identities are here to make your work easier. So they are not yet, they don't exist to make you suffer or anything. They are supposed to make your work quite easy. So now, look at the question we have right in front of us. We have, in this case now, it's written as ln 3x. So we are told we want to go on now to solve this. All right? We want to go on to solve this. How do we get this? These are very interesting questions. You can see them tomorrow. So please, I'm begging you, if you're really paying attention, please pay attention very well. All right? Now, ln 3x. We want to use first principle to solve ln 3x. Of course, it's the same process, the same steps. What's the first thing you want to do? You want to increase the x and y variable. I'm sure nobody argues with this. This is basic. We have done this several times today. And I'm sure you understand what's going on. Good. So what we have to do next is to make change in y the subject of formula. And this will be ln 3x plus change in x minus y. And then we have change in y being equals to ln 3x plus change in x minus ln 3x. I believe we all agree with this. Now, let me remind you of something. Do you remember in logarithm? Because I hope you know that ln is natural logarithm. I'm sure everybody here understands that. I don't think you are saying ln as one bizarre, one strange expression. That's just the short for natural logarithm. Now, the laws of logarithm works with it. Remember when we were dealing with logarithm and we say log x minus log y. What do we say this is going to be equals to normally when we're dealing with logarithm? We say this will be equals to log x over y. This is a law I believe everybody here agrees with, right? Good. So since you all agree with this, that means it's not wrong if I write it this way. Ln 3x plus dx over 3x. I'm sure nobody disputes this or is looking at this as a strange thing. This is the law of logarithm happening right here. I've not cheated at all. Now, I'm also sure that you agree with me that under algebra, I can cancel 3 out here. So I've not done anything wrong if I decide that I want to cancel out the 3 here, because 3 is common here, 3 is common here. I can cancel both of the 3 out there. So that means I can have this expression as change in y equals to the natural logarithm of x plus change in x over x. All right, making sense? Good. Now, look at what we're going to do next now. We're going to go to step number 3. What is step number 3? Quickly, we want to go on to divide by change in x. Change in x, change in x. Or you can go on to write it as division. But you know what I'm doing right here. I'm dividing both sides with change in x. Now, look at what I want to do now. This is where it's very essential you pay attention, because once you lose your focus at this point, you will start asking questions on what happened. Now look at it. I'm sure you all agree with what I've done now. I went on to make the y subject of formula, change the y subject of formula. Then I went on to divide both sides with change in x, which is what we have always been doing. Now, I'm looking at something going on here now. Guys, pay attention. And this is what's going on. I want to find a way. I'm looking for a way to try to see this. I want to see this happen, because I know that I will be very safe if I can make that to happen. So look at what I want to do. Please just pay attention. Don't worry. I'll make it as simple as possible. So look at what we have here. There's something I'm going to do. I want to this is what I'm trying to gun at. Let me do something quickly before we, let me just write this. Let me try to express this a bit more simpler. This will be ln x over x. Do I need to write that? Okay. For those of you that may not, over change in x over x, and over change in x. So all this return to 1. I'm sure you agree that x over x is 1. So good, 1. So this is much better to see. So now, look at this now. This is 1 plus change in x over x. Look at something right here. This and this, don't forget, it is the limit of this. So, you know, u here can represent anything. I'm sure you guys agree with me. U. It can be anything. U can be literally anything. But if you look at what's going on here, I can see u here, I can see u here. That means dx over x, dx over, there is no x here. That is what is making this not conform with this. This looks very similar. 1 plus something. Understand that the u here doesn't mean it has to always be u. 1 plus something over that same thing. Now, this is 1 plus dx over x over dx. What if I could have an added over x here? That means this will conform to this. You know, your identities make your work easier. Once you remember when we were doing the previous work, once I saw sign change in x over change in x, I want to bring them close to each other, because I know that sign change in x over change in x will give me 1 automatically. So we don't, in questions like this, you don't just solve anyhow. You solve knowing many things, and then you use those things to work. You use those things to make your progress. Now, I know this identity now. That's why I didn't rub it off so that you can see it. I can see that this is 1 plus something over something is equal to 1. If I'm able to achieve that this thing and this thing are the same thing, then I'll be able to achieve this, and all this return to 1. So you see what I'm going to do now? I'm going to try and get there, because that's mathematics for you. I'm going to try and get there. So I'm going to multiply the denominator with 1 times 1. All right, I'm going to say dx times 1. And somebody will say, okay, if I multiply by 1, so what's going to happen? You see what's going to happen? If I multiply change in x by 1, I have not done anything wrong. It's mathematical, right? It's mathematical. So it's like saying, look at what I want to do, and I'm sure none of you will say I'm wrong. I want to multiply this with 1. Don't forget what I'm trying to aim at. I want to see this and this look alike. This, what I have here and what I have here, look alike. Because I can see that you and you, once I'm able to achieve that, I'm going to be getting to 1 as my answer. So I want to make this look alike. So I want to multiply this with 1. So I'm sure you guys will say I'm not doing anything wrong. But you know what I'm going to do? Instead of writing just 1, I'm going to do something else. I'm going to write x over x, right? Nobody is there saying I've cheated, right? I'm still doing something right because x over x is 1, right? So I've not done anything wrong. So good. Keep watching. I have ln 1 plus change in x over x. This is still there. Now I can have change in x over x, of course, times x now, which I'm still very correct. So now, look at what's going on here. I want you to know that what I wrote there is the same thing as this. So let me bring my change in y over change in x is equals to 1 over x multiplied by ln 1 plus change in x over x over change in x over x. See what's going on right now. I'm sure nobody disagrees with me. See, in case you are having issues with understanding what I just did, what I have here, of course, you see that this is this is this, then this, it's 1 over x. You know, it's all the same thing as 1 over x. So I just wrote it here. You can see that. So what I wrote now is still the same thing as what was here, only with a different flavor, with a different form. So now, I look at the step that brought me here. I multiply by 1, which my 1 was x over x. So I brought this x to this dx over dx, and I took this x outside. So now I've done something that makes me feel quite happy, because I'm already seeing something that makes my work easy. Because right now I can see that I've been able to conform this my expression to look like this. Now I have ln 1 plus something over that something. It's conforming already. So I'm good to go now. So look at what I'm going to do now. Now I can go on now to my step number 3. Sorry, my step number 4 rather. What's my step number 4? My step number 4 is to take the limit of both sides. Change in x tending to 0. Change in y over change in x is equals to 1 over x dot. I'm bringing that one outside because I just don't feel it. If you take the limit of this, it's still going. If you take the limit of, because some people may not understand, let me still talk about it. But again, okay, this is what I'm going to do. I don't like people getting confused. It just doesn't serve the reason why we're here. So let me act like nobody understood what I was trying to do. Let me just do it straight up directly. So 1 over x dot ln 1 plus change in x over x over change in x over x. So I think this is still better understood. So I just took the limit of both sides. So what I wanted to do now is all this return to the y over the x. The y over the x is equals to, now it's like taking the limit of change in x tending to 0 of 1 over x, then the limit of change in x tending to 0 of ln 1 plus change in x over 2 over change in x over x. Good. I've splitted it. This will be the same thing. The y over the x will be 1 over x. That's what I wanted to do. But people will be asking, what am I doing? Like, what did I do? How did I get there? That's why I needed to re-express it so that nobody is asking those questions. So, all right, look at what we are having now. So in this case now, you can see that this whole thing now will turn to 1.1. And that means invariably that the y over the x will be equals to 1 over x. Oh, thank you, Jerry. Thank you, that person. Thank you. Thank you very much. Over x. Can you see how nice this is? That's how nice, if you can flow with all these things, you are very much on the right in the right place. So this is how you solve all these things without making mistakes. So you just need to have basic understanding. So we don't have time, so I have to you almost don't have time to even take a breath or something. But that's because we are moving with time, and I want you guys to, because your exam is coming, and I want you guys to really make it really great. So that's why I'm trying to be quick. So y equals to e raised to power x plus 1. Can you try this? Can you try this? Can you try that? Y equals to ex plus 1. Can you try to use first principle here? Don't forget, there's an identity I wrote here for you. So this will come in handy at a point. All right. So try and solve this one. Guys, it's time to, just act like you're in an exam hall. Imagine this was your question. What are you going to do? Imagine this was what you saw. And they just told you, using first principle, find the differentiation of this. Differentiate this. So just imagine you are right in that situation. What are you going to do? So try and solve it, so we can solve together also. And then when you make a mistake, we would correct it together while solving. I'm sure you guys are really enjoying this, because this is you getting real and explanation. I don't think anything we have said today is controversial. I believe everything has been much direct. So I don't think anybody should be having any issue at all. And if you have any issue, you can always reach out, obviously. But I think it has been quite clear. So can you try and solve this? Can you try and solve this? How do you get your answer? You have to find the y over the x right here. So guys, of course, I'll be doing mine. You can be doing yours, so that you can compare and construct what we're doing. If it's the same thing, if you are having a mistake, you can correct yourself. So I believe the first step is for everybody to know it's not going to change. It's the same thing. Wherever you have a question, just when you are using first principle, just follow this process. Increase both the x and the y variable. All right. So now we have change in y equals to e raised to power x plus change in x plus 1 minus y. The same process. I believe you can all flow with me. I'm sure you understand what we're doing. It's not something you cannot solve. It's something I'm sure you can solve. So look at what we're doing right now. We go on now to make our y what y was. And that will be e raised to power x plus 1. All right. I believe everybody could flow till this point. Is anybody having any issue? So look at it now. We can go on to have change in y equals to e raised to power. We want to bring x and 1 together. So let me write x plus 1 plus change in x, just so that nobody is asking me what I'm doing. So I can see x plus 1 here. I can see x plus 1 here. So what I want to do is I want to apply that rule of indices. I'm sure you guys remember this rule. The rule that says e raised to power x plus 1 times e raised to power change in x. I'm good to do that. There's nothing wrong in me doing this. I've not cheated. I've not done anything wrong. So now that I've splitted it, now I can see e raised to power x plus 1 here. I can see e raised to power x plus 1 here. So I can obviously group this as e raised to power x plus 1. Then open a bracket, and I'll be having e raised to power change in x minus 1. All right. I'm sure you guys are flowing. It's step by step. You want to understand calculus, understand all your identities, and move step by step. Just do things the right way. It's not as difficult as some of you make it look like. It's very simple. So the next thing now, we've done step 1, we've done step 2 successfully. Let's go on to do step 3 now. What is step 3? Divide both sides with change in x. So we have change in y over change in x will be equals to e raised to power x plus 1, e raised to power change in x minus 1 over change in x. All right. So now look at what we have here. I'm sure you know that I can split this thing. I can split this fraction this way and I won't be wrong. E raised to power x plus 1 dot e raised to power change in x minus 1. Let me put this in a bracket over change in x. I'm sure you know I can do this and I have not done anything wrong. All right. Now, let me clean up this place so that we can use this place. Are you guys flowing? I'm sure you guys are flowing with us. So I've done step number 1, step number 2, step number 3. I want to do step number 4, which is for me to take the limit of both sides. I want to take the limit of this side while change in x is tending to 0. So I have change in y over change in x will be equals to the limit of change in x tending to 0. This is the secret to success. If you follow us through in all these classes, you cannot go wrong. So I want to split it straight up. I want to split it straight up because I don't want us to have to be split into writing it twice. I want to write, I've written for this one, I've taken the limit of this one, I want to take for this one now. So I have e raised to power change in x minus 1 over change in x. Good. I'm sure you are flowing. Please don't mistake this. This is a different thing entirely. Right? So now what do we have right here? Is somebody seeing something? Are you seeing something? We have this identity that said when you're taking the limit of this tending to 0 of e raised to power the thing minus 1 over, are you seeing something? All this, you look at it right here. That's what's happening right here. If you can see it, you can see that in this case now we have e raised to power. Now, of course, it doesn't have to essentially be h. It could be any other alphabet, it could be any other thing. So taking this as h, of course, you can see that all this will turn to 1. So obviously now, don't forget also that all this turns to the y over the x. This will be equals to the limit of this. This is a constant, I hope you know, because there is no change in x here. So this will be the same thing as e raised to power x plus 1. There's no change in x here, so nothing is going to happen. It's just going to be the same thing. Dot 1. So obviously the final answer will be e raised to power x plus 1. This is just the way you solve questions, and it looks like if you're not very smart enough, it will look like you are dealing with a very complex question. But when you pay attention to it much closely, you will notice that it's quite very simple. Guys, I don't want us to carry these two questions over. It's not very long. Let's just try and do it. We're not clocking it yet, guys. We're not clocking it. Let's just give a few minutes. Just a very like we want. I don't want us to start off with this tomorrow. It's one of the things I explained, and it will be good if we move in the same flow. All right. So it's very very important, and it's a likely question for your test. Log EX. I want us to try this. Look at this. Can you find this question? Will actually some of you may not get it, and I would love to see what you are going to actually do. So what's your answer to this? Now I'm going to take you through two. Okay, do I just do for the one of EX? Let me do for log EX plus 1 first. It's the same thing, but I want to do for X plus 1 first. Then we'll go back to do for EX. Let's do for X plus 1. So whichever method you want to use, apart from, of course, using first principle, but there are two different directions we can take. And I prefer there's an easy one, but I really hope you, let me see which one you're going to take. What's the answer to this? You are using, no, I don't mean you should use, I mean use first principle. Use first principle, guys. Use first principle. You guys are using the general way. Use first principle. I don't mean you should use, I understand what you guys are doing there. Don't use don't use the general way. Of course, for those of you that you are asking and you're wondering how they were able to get the answer quickly, if you remember your what I explained when I started, I'm sure you know that I could write y as equals to ln x plus 1. By the way, you can still go on to solve this without changing it to ln. We probably can do that, but I don't know if you're going to do that, but let me change it to ln. But if you don't have to change it to ln, you can still solve it. So, and if you use ln, how do you go on to solve this using ln? Or probably we should use without ln, since we have used for ln before. I don't know, or probably let's use for ln first. I don't know, I want to give you guys the best, but I'm looking for the one you prefer. So probably let's just use this. But I would have loved to try the other way around, so that for those of you that probably you may not remember this, you probably can still move without having to change it to ln. So, but no problem. Let's just this is the first step. I'm sure everybody knows this. The next step, changing y equals to ln x plus dx plus 1 minus y. Changing y will be equals to ln x plus dx plus 1 minus ln x plus 1. Of course, because I have changed log base e to ln. So now at this point, I'm sure you know what to do. I don't need to re-mention it. If you followed us in the last question, the law of logarithm will work here. We'll be having ln x plus change in x plus 1 over x plus 1. I'm sure everybody agrees with this. So it's very okay if I wrote it like this: x plus 1 plus change in x over x plus 1. And if I go on now to write it like this, I would not be wrong. Can you see the way even your initial arithmetic is very key? I'm sure you guys should be able to flow with everything I'm doing. I'm not doing anything that I'm sure you should be able to flow with what we're doing. This is obviously me just using, this is just normal. There's nothing I'm doing here that is very difficult. So change in y is equals to ln 1 plus change in x over x plus 1. All right. So now, this is where it gets, somebody is talking about being lost. What I'm doing here is basic. Ln x plus 1 was what we had normally. That's from here. So I added the x to both sides, and then I made the change in change in y subject of formula. Then I went on to substitute y for this back. And then applying the law of logarithm, I have this over this happening. So look at this now. This is x plus 1. I brought it to this side. Then plus change in x plus 1. I just rearranged it. All I did here was rearrangement. All right. So now I splitted the fraction to be x plus 1 over x plus 1 plus change in x over x plus 1. I splitted the fraction. Then this and this will go. To, you will left with 1. Then this is there. So that's where I'm still at. So if you look at what we are doing now, so we have gotten to that place now. So we can go on now to step number 3, which is for us to divide through with change in x. So I can go on to even do it here. I can change in x. Then I can say divided by change in x. So that means I will have change in y over change in x is equals to, of course, this will turn to times 1 over change in x. I'm sure you agree with that. So I can have it as 1 over change in x ln 1 plus change in x over x plus 1. I'm sure you understand what I'm doing. If you're writing, you will be able to flow. Just follow the mathematics. It's quite very simple. All right. So now look at what we want to do now, which I would love you to really pay attention. This place now, if you don't pay attention, you will ask me, what did I do? I can assure you. So look at, again, I'm trying to see if I can conform anything going on here to something like this. That's what I'm trying to see if I can do. Of course, there's a limit here. So now I want to conform this to this. Look at the approach I'm going to take. Please pay attention. If you don't pay attention, you may have some issues. Look at this. So look at what we have here. I'm going to represent it with any letter or any letter. I probably will use U. And if you don't want us to use U, you can use any other thing. So let U be equals to change in x over x plus 1. There's a reason why I'm doing that. You will understand why now. So let U be equals to that. So of course, that means I can say change in y over change in x is equals to 1 over change in x, the natural logarithm of 1 plus U. I'm sure nobody is here disputing that input. Now, from what I wrote there also, if change in x, if this was equals to this, that means from here, from what I wrote here, change in x is equals to what? U times x plus 1. Because I just cross multiply. Look at change in x is equals to U times x plus 1. That's perfect. So that means I can also go on to change this, my change in x here, to this. So I can have change in y over change in x is equals to 1 over U x plus 1 ln 1 plus U. Now, look at what I was trying to achieve, which I'm sure some of you have seen already. You have probably seen it already. You see that I can easily bring this U here now to this side, and I'll be looking at my identity coming out, if you understand. So now I can have change in y over change in x is equals to, I'll just have it x plus 1 here, and I will shift this U, which is still the same thing, it's division. So ln 1 plus U over U, still the same thing, I just rearranged it. So you can understand what's going on. So it's just, majorly you have to know how to change forms and adjust things in calculus. You just need that skill. Now, I now want to do the last step, which is for me to take the limit of both sides. So I take the limit of this as change in x is tending to 0, change in y over change in x That will be, of course, I don't need to write this again. You know this will be a constant, so I can just write it like this, please. But I'm sure by now you should understand what's going on there. It's a constant, so automatically it will still remain the same. Look at that. So all this will turn to the y over the x. So the y over the x will be equals to, this will be 1 over x plus 1. All this will turn to what? 1. So that means the y over the x here will be equals to 1 over x plus 1. Are you really seeing that now? That's how basic this is. So what I'm going to do now is that I'm going to solve the last question now without using this format, so that those of you that wanted to move without this format, this is the last question for tonight, the one I want to solve, and you will not need to follow this format all the time. So I can clean this identity now, but of course you can use whatever I want to do, whatever I want to solve. You can use this other method, but it may not even be very easy with this other method. But let's just see. The question I want to solve is the question I asked before, which is y equals to log e of x. This is the question I want you to solve. Now, I'm sure if you place this normally without even, you know that if you differentiate this, you get, of course, it's better you write it as y equals to ln x if you wanted to use the normal general way. And if you differentiate this, the y over the x here, this is like an identity. You should see it in the table, will be 1 over x. This is something you should know normally. You should know this normally, that when you differentiate ln x, you get 1 over x. You should know that. That's an identity you should know. And you should remember that log base e, x is the same thing as ln x. All right. So this is settled. You can do this is straight up. You know this answer already. But let's try and use the first principle now to solve this. That's the real point, because you know when they ask you to use first principle, it doesn't mean you don't have a quicker way to solve it. It's only that they wanted you to apply the principles, the first principle. So let's use the first principle now to solve this. And I don't want to move changing it to ln x. I want to use the normal y. Y is equals to log e. We're going to use something called Taylor's series. And that Taylor series is why I want to explain it, so that in case you may need to use Taylor series in any of your other questions, you will not be too disturbed. So it will serve you well for me to do this. Now, if you look at this is the question you're supposed to solve this using first principle. Now, what you want to do here is to go on to do the normal thing, which I'm sure you remember this in logarithm, that e raised to power y here is equals to x. You can write x equals to e raised to power y. Now, look at this. This is more like a change in the form, different from what you have always had. All right. So you want to go on to do the increment. This thing I did is something you should know already. E raised to power y equals to x. It's a law under indices and logarithm, which I believe you should know. The base raised to the power of this is equals to this. Now, what you want to do next is to increase both sides. That will be x plus change in x will be equals to e raised to power y plus change in y. If you're noticing, it looks different at this point, but you still need to keep moving on. So what do you do next after doing this? Of course, you want to make, in this case, the hexagonal formula. Guys, just don't worry. Just stay put. You will understand what we're doing. This will be e raised to power y plus change in y minus x. You will say, why are we solving for change in x? This is different from what we have learned. Of course, you will see at the point we will still make the reciprocal later. And when you know what we're heading to, let me quickly say that what we're heading to is, when we're done doing for change in x, we will not divide through by change in y. So let's assume, for instance, let's say if we do this, we're going to get x as our answer. But don't forget, we're not trying to find for change in x over change in y. So this will have given you the x over the y being equals to x, which is not what you are looking for. So you will invert it, you will get the reciprocal, and the reciprocal dy over the x will be equals to 1 over x. That's the way it's going to work. So we're going to move steadily, and then we will arrive at wherever we're going. So look at what we have here. We'll solve like this, then do what I just explained. So what we have here, you have to go on to change minus, what was our hex? Our hex was e raised to power y. right? So what do we have next? What we have next is we can make e raised to power y the subject of formula. Sorry, we can factorize e raised to power y out. That will be e raised to power y. Let me do it this way first. So change in x is equals to e raised to power y, e raised to power change in y minus 1. Now, this is now the place where you will be needing to use your Taylor's series. All right. So I want you to know that by default, this is the expansion for Taylor's series. By default, the expansion is wherever you have e raised to power x. By Taylor's series, we have it as this. So by default, if you are doing for e raised to power change in y, you will just be having 1 plus change in y plus change in y square over 2 factorial plus change in y cube over 3 factorial plus dot dot dot. Now, what you have to do is to go on to fill this using, what you have here. You go on to fill this into this pot. You go on to fill all this into this pot, and then you will be able at that point to solve your expression. Please, can you confirm if you are following me? All right. So look at this is Taylor's series expansion. What I wrote here. This is not something you need to understand. Just get this known. Now, when you have e raised to power x is equivalent to this by using Taylor's series. So when you have this e raised to power change in y, of course, e raised to power x is this. So that means e raised to power change in y will be this, obviously. So you want to put all this now into this place. All right. That's what you want to do. You want to put all of this expression. Let me clean this. So you want to put all of this expression now. That means you want to say change in x now is equals to e raised to power y. Then you want to put in all these things here now. That'll be 1 plus change in y plus change in y all square over 2 factorial plus change in y all cube over 3 factorial plus dot 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 on and on and on. Then don't forget there is something here, minus 1. After you are done with this, there's still a minus 1 here. Don't forget, because all what you have here is just the expression for e raised to power change in y, this one. So there's still a minus 1 which you have to put here. And if you can look at what is going to happen, there's a 1 here, there's a minus 1 here. This 1 will cancel this minus 1. So you'll be left with change in x will be equals to e raised to power y. Now you'll be left with change in y plus change in y square over 2 factorial plus change in y cube over 3 factorial plus on and on and on. So this is how you apply Taylor's series while solving questions like this. I just needed you to be able to move like this also. I don't want you to be so that you don't get cornered when you have a question that requires you to use this. So what's the next thing for us to do? The next thing for us to do now is that we want to divide through with change in y, because you know that that's the next process. But of course, I told you already, you remember when I was discussing this, you will now divide through with change in y. So we're having change in x over change in y being equals to e raised to power y, of course, all these things. So, okay, let me just write it because we'll be needing it. Now, I'm dividing all these ones with change in y. So look at what will be happening. It's like, if you wanted me to do it better, I would have just said factorize change in y outside. So if you factorize change in y outside, imagine we had, let me write this smaller, equals to e raised to power y. So I want to factorize change in y outside. So if I factorize change in y outside, this one will be left with 1. I will not have this anymore. There will be 1 here. This will just be not more raised to power 2, just the normal change in y. This will now be raised to power 2 because I brought 1 outside. I'm sure you all flow with that. That's just normal factorization. And then this change in y will now cancel this change in y. That's just, I'm a bit in haste now because I want us to close this class any moment from now. So e raised to power y, then I have 1 plus change in y over 2 factorial plus change in y square over 3 factorial, and so on and so forth. So what is the next thing for us to do? We can now go on now to take the limit of both sides with change in y tending to 0. All right. So taking the limit of both sides, change in x over change in y, change in y tending to 0. Change in y tending to 0 now equals to the limit change in y tending to 0 of this e raised to power y 1 plus dot 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 dot. I don't want to have to write all those. I'm sure you understand. It's this whole thing I wanted to write there. So what do we do now? You apply the limit. Now, when you apply the limit, of course, this video will be available for you to go back to, and you'll be able to pause it at that point. When you apply the limit for this one, what will happen is that you'll be having the x over the y. Of course, taking the limit of this. Then in this case now, you want to fill in the y as 0 in all these things. So the y as 0 here will be 0 over 2. Look at 0 over 2, 0 square over 3, you know, on and on and on. I'm sure you can see what we're talking about. So we will have 0. If you put 0 here, you'll be having e raised to power y 1 plus 0 over 2 plus 0 square over 3 factorial factorial, and so on. So obviously the x over the y will be equals to e raised to power y. I'm sure everybody agrees with that, right? So if the x over the y is equals to e raised to power y, this will mean that the y over the x, I told you already, we will now be inverting. The y over the x will be equals to 1 over e raised to power y. Now, let me show you this was log e. This was the question we had. Don't forget, because I have rubbed it off. But let me write it here. When we had this question, don't forget we said x equals to what? E raised to power y. Do you remember when we started? This was what we wrote. So that means e raised to power y is also x. So wherever we saw e raised to power y, we'll be writing x. That'll be 1 over x. That means the y over the x is equals to 1 over x. So guys, thank you very much for joining. This will be the last video on the last question for today. I hope you were able to follow through on what we did. This video will be released by God's grace tomorrow. You will have the opportunity to go through them. So this tomorrow we'll be going deeper. There's so much exponential, logarithm, probably hyperbolic, and every other thing. On quotient rule, product rule, we have a lot to deal with. So guys, thank you very much for joining. It's been an amazing moment. I can say we have been able to achieve so much today. Today was quite very intense. So okay, somebody said I should have done this one tomorrow. Well, I just didn't want us to, I don't think I wanted us to be talking about this tomorrow. I just felt let's just get this through today, because we have so much and we have to move with, we have to be timely also. But anyway, if you were not able to follow through perfectly, you will get the video released very soon. So guys, thank you very much. It's been an amazing moment. Make sure you try and revise all of this and prepare very well for the test happening tomorrow. Next week. Yeah, tomorrow is next week, but anyway, next week. So guys, thank you very much for joining. Thank you. Thank you very much. Have a good night.